we're going to talk about alkenes and their properties and review how to make alkenes before we move on to the reaction of alkenes. So where we last left off, we talked about alkenes and how to name them. And we talked about the cis-trans and the E and Z system. We'll just briefly mention their commercial importance and go on from there about the stability of alkenes. So the reason alkenes are so important is, let's just take a start with ethene, or more commonly known as ethylene. And one of the most commonly used items that we have is polyethylene, like polyethylene shopping bags, and that's basically polymerized ethylene. What that means is that I have many ethylene units, so it's not just one, but normally this N goes to the thousands. And with these long polymer strands, we can actually use them to form materials. Okay, if you oxidize it and continue to oxidize it, you can go to formaldehyde, or not formaldehyde, acetaldehyde, and then to acetic acid. This is used quite frequently. When we talk about aspirin, you can put chlorine on it, and then from there, make vinyl chloride. You can just basically add water across it and make your ethanol. You can also oxidize it and make epoxides, which, as you know, with the epoxide resins, we use a lot of epoxides in glue, and this can form, you can also use this to form epoxides to form ethylene glycol, which in the past we used quite frequently as radiator fluid, but because of its unfortunate toxicities, we've now moved on to propylene glycol. So, but we can use ethylene glycol. Let's talk a moment about the stability of alkenes, and I think we mentioned it briefly before. Basically, if you look at alkenes, this is 1-butene. This is trans 2-butene. And what we find is this one is more stable. Okay. And if we continue to look at substituent effects, what we find is the following. Mosaic says, it's the more substituted, double bond, is usually more stable. Okay, so let's give you a couple of examples. If you had to compare 2-methyl 1-butene, and compare that with 3-methyl 1-butene, which is more stable. So what you need to do is let's draw the structures out so we can make a comparison. So here is 1-butene, 2-methyl, so 1, 2, 3, 4, 1 butene, 2 group, 2 methyl. So let's do the same. 3 methyl. Here's 1 butene. 1, 2, 3. So you can see that this double bond only has 1 substituent. This double bond has 1, 2. So this is more stable because it's the more substituted alkene. Let's talk about cyclic alkenes then. Or let me just talk about cis-trans. I think we've mentioned this previously. If we look at cis 2-butene versus trans 2-butene, let me just say, okay, you can see that the groups here are closer than the groups here. What that means is that for the trans, it's more stable. Now, how does this compare when we say, oh, let's just take a look at something like, this is 2-butene. If I look at 1-butene, because I have 2 substituents on the double bond, these are both still more stable than 1-butene. Okay, so just so you're aware, this is like a finer gradation, okay, with the cis and the trans. Okay, so you have an idea about how to evaluate what's stable and what's not. If I looked at a 3 substituted double bond, that's even more stable than 2 substituents. So even though we have this difference, they're both going to be less preferred, less stable than a double bond that has 3 substituents on it. Looks like a cycloalkenes now. Okay. When we look at something like a cyclopropene, remember, this hybridization state, this is an sp2 carbon. So your bond angle should be 120 degrees. But instead, 60 degrees. Okay? So for the longest time, it was considered that this type of structure is not possible. Okay? However, just so you know, it's in a natural product called uric acid. Contains this group. However, if you ask, is it reactive? Okay, it's unusual. All right, and it opens easily. So, however, it does open easily. So that's a cyclopropene group, and we know it has a lot of ring strain. If you look at cyclobutene, this also has a lot of ring strain. Okay. If we look at something like cyclopentene, okay, this is much more favorable, all right, over cyclobutene. And then we have cyclohexane. But notice the one thing is when we name these, we don't use cis or trans. And the reason is for rings, for cycloalkenes, less than 8 carbons, all double bonds, are cis. Okay? And we have 8 to get a trans. It's not the most favored. Typically at 10, you'll see the more favorable ones. Okay? So, no trans because of ring strain. Okay? So just be aware of that. Alright, now let's give you a couple examples of your rings. Okay? So if I gave you one, two, three, 4, 5, 6, 7, 8, 9, 10, this is a cyclodecene. This one is a cis. Okay? Now when I do this, be aware this is a trans cyclodecene. Okay? And they're almost the same stability. And remember, this is because I have a 10-membered ring. A 10-membered ring. Okay, before I start getting some reasonable stability by having a trans double bond in my ring. Now, if we take a look at our bicyclic systems, okay, again, you can't have a double bond and a bridgehead carbon unless one of the rings contains at least 8 carbons. So, if I looked at a system like this, okay, this is unstable. Okay, just because of the strain at the bridgehead carbon. All right, right? Now, if I did this, this is acceptable because double bond is not at a bridgehead carbon. Okay, so you see the difference? That one's not. This is my bridgehead. This one's too small. Let me give you an example of one that's basically stable. If I gave you something like I put double bond right here. Okay, this one is stable. Okay, at the bridgehead carbon. Okay, why is that? Because let's do a count. Suppose this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have more than 8 carbons in one of the rings. Because of that, the larger size ring allows you to have a stable double bond at the bridgehead carbon. Okay, so let's take a look at these guys. Okay. Messy. Easier to see. Right. This one. Review. All right. So of these structures, which ones are stable? So if you look at this one, 1, 2, 3, 4, 5, 6. 6-membered ring. 1, 2, 3, 4, 5, 6. 6-membered ring. 1, 2, 3, 4-membered ring. This double bond is the bridgehead of carbon. So the ring, the maximum size, ring size is 6 carbons. Double bond at bridgehead. So, not stable. This one, on the other hand, my double bond is not at a bridgehead carbon. You can see it's a cis already. So this is stable. All right? This one, 1, 2, 3, 4, 5, 6, 7. It's only 7. So basically, not stable. Again, the bridgehead carbon, but like the first one, it's not 8 carbons or so. All right? So, let's talk about a couple of other things about physical properties of alkenes, and then we'll move on to how to make them. And that'll be a review for you. All right, so the physical properties. Their densities are all less than 1. But not surprisingly, is it? I mean, the organic substances that we work with always going to be less dense than water. Only time it's more dense than water is when we have an alkyl halide, right? With at least 2 chlorines or more, or if it's an alkyl bromide or alkyl iodide. Okay, if you look at the polarity, very, very, very slight. They're essentially nonpolar. Okay, so at most you only see like a 0.33 to bi, just because there's some pull to stabilize my double bond. And the reason is my pi bond, okay, is polarizable. And this property is important because what that means then is when you have this stabilization, this has more electron density, it's polarizable. So when we start talking about reactions of alkenes, we'll see the double bond that is going to be doing most of the electrophilic attacks. Okay, so why don't we stop here, and what we'll do is we'll start talking about how to make alkenes.